This is a presentation of the PCL Gold 4.01 features. The PCL objective is to deal with complexity in a pipe stress analysis only when you need it. We make most PRG consulting runs here at PRG using Caesar 2 since that's what our customers ask for. If the model's overstressed, close to an equipment allowable, if we have difficulty with friction convergence, if we have multiple load cases, a high number of cycles, acoustic induced vibration, refractory or glass-lined pipe, or we have a loading condition that Caesar doesn't analyze, which is pressure cycling, for example, then in those cases we use the PCL and Caesar. A few sections from the 2010 version of B31.3 are shown here. Included in these equations, which are of a similar form to those given in Appendix P, is the inclusion of the stress indices for axial loads and torsion. It's written here that this is the responsibility of the designer to determine sustained stress indices when not explicitly in Appendix D. Torsion, pressure, and axial load I factors are not in Appendix D. So for pressure, axial, and torsional sustained stress indices, we're told that in the absence of more applicable data, IT and IA, which includes the pressure stress indices, can be taken as one. Now the question we have to ask is there any more applicable data for pressure? If we go to Annex 5.D in Section 8, Division 2, we're given stress indices for pressure for nozzles in certain geometries of cylindrical shells. The stress index from Section 8, Division 2 is not 1, it's 3.3, but it is based on the membrane hoop stress in the vessel, which is PD over 2T. The B31.3 pressure stress index that we saw on the last slide is based on FA over AP, which is the longitudinal stress in the pipe. AP is the area of the branch for the branch evaluation and the area of the run for the run evaluation. For Section 8 Division 2, the areas and the wall thicknesses are for the vessel, or for the run always. So we're given what should be considered applicable data in Section 8 Division 2, but it's not in a form that's directly comparable to the B31.3 required sustained stress index. Now, I mention this example because it's important as we go to other sources for B31 data that we develop an apples-to-apples conversion. So we're improving the stress calculations, but if we look at Appendix D, the K factors for branch connections are all 1. Although Note 1 to the Appendix D Table D300 states that flexibility factor data are only for use in the absence of more directly applicable data. So do we have more applicable data for the K factors? In a previous webinar, we looked at numerous examples where more applicable data was arguably available. For the model above, we used rigid, or K equals 1 for the top model, FEA for the middle model, and a pinned end for the bottom model. So in this case, a pinned end might be more applicable data. Now if we look at the comparisons of these two results on the next slide, we can see that the pinned end gives as reasonable or a similar result to the finite element calculation for the stress at 30. So what may be more applicable for a certain system may be as simple as assuming that the intersection is a pinned end. In WRC 329, Ev Rodabaugh talks about how the K equals 1 guidance in the B31.3 code may be inaccurate. Mr. Rodabaugh says that the inaccuracies may be greater than that due to any of the inaccuracies in the I factors. So the question then becomes, where can we get more applicable K factors? Section 3 has provided correlations for in-plane and out-of-plane K factors for more than 40 years. Rodabaugh in a variety of EPRI documents has published them, as has PRG in Peter Vu's 2011 ASME paper given in Fayetteville, Arkansas, as has Dr. Wydera in several papers. Some examples of these K-factor calculations are shown in the next slide. This is a form available in the PCL and from Nozzle Pro that shows a variety of what may be more applicable I factors and K factors for branch connections. The geometry shown here is a standard wall 8 by 12 inch branch connection. welding tees, pad reinforced tees, unreinforced tees, sweepolets, olets, and thickened nozzles are shown here. Comparisons are given to the Section 3 code, DNV, EPRI and the Weiss Rotobaugh documents, and WRC wide area equations. We can see for the unreinforced fabricated tees that each of these methods agree that the value of KOB is about 17, which is much different from 1. So the question is, should we use K equals 17, and will it matter? Mr. Rotobaugh gives an example in WRC 329. For the 30 by 12 inch intersection in his example, KOB is 65. So the analyst must make the determination if this K is more applicable than 1 and if it will make a difference in the result. In the WRC 329 example, including the K factor in the analysis changes the calculated moments by 9 times. Mr. Rotobaugh goes on to say that this is extreme, but that greater accuracy in code evaluations are not achieved without more accurate K factors used along with more accurate I factors. The PRG opinion is that you don't have to use K factors in an analysis, but that you should evaluate them. Most programs, Caesar included, and the PCL, have correlation equations to help with finding more applicable K factors. We think that the code, B31.3 and B31.1, are telling the user to at least evaluate the K factors and then decide if they're more applicable. Are they different from 1? You just look at its value or look at the K factor value and then look at the piping system and decide if the extra equivalent pipe concentrated as a point spring at the intersection will have an effect on the analysis. In the example system above that was used in WRC 329, our KO was 65. So we have 65 extra diameters of 12-inch branch pipe. That's 780 inches of length concentrated at the intersection that reduced the moment by 9 times. We can see in the sketch that the overall pipe length was 240 plus 120 inches or 360 inches. So we'd expect an equivalent 780-inch length concentrated point spring at the intersection in the out-of-plane direction to have an effect on this piping system. And indeed it did 9 times. The VU paper for this intersection gives a KOB of 65. Section 3 for the Ev-Rotobaugh intersection gives a KOB of 46. Dr. Weiss of 53 and Dr. Wadira in WRC 497 gives a KOB of 81. Note that in this spreadsheet that KOB for Appendix D is blank, and that represents the K equals 1 in Appendix D. So the question is not so much, do I have to use these factors, but should I use them? So where the K factor is greater than 1, you should probably look at the configuration of the piping and decide if a K times D length of pipe concentrated at the branch will affect the results. If it will, then maybe you should use it in the calculation if load redistribution in the system is important. Where the piping configuration is not just an anchor-anchor system, when K factors are used, the displacements will likely increase and the loads will be redistributed. We'd rather not have to deal with all this K and I factor complexity if we don't need to, but we would like to have the capability of dealing with it if we have to, and that's what the PCL is for. Most pipe stress analyses don't require pressure I factors, or more accurate friction calculations, or refractory or glass stress calculations, or flexibility factors for branch connections, but some do. In some large diameter, hot piping systems where temperature controls the flexibility design and pressure is low, i.e. where the D over T is large, and there are multiple thermal configurations and a high number of cycles and potentially small attached branches and guides with gaps, then flexibilities and more accurate I factors and a detailed analysis can be important. So the PCL is designed to default to the simple, but to allow easy activation of the complex if needed. So we think you can tell a lot about a program by its input. So as an example, what we tried to do with the PCL was let the user enter the number of turns on the rubber band if that's all he happens to know. But if the user knows more about what might affect the flight, we let them put that in the program too. So you can tell a lot about a program by its input. So let's take a quick look at a few of the unique items of input for the PCL. First is the allowable refractory tensile and compressive strength, which are different typically by about 10 times. When local areas of the refractory in the analysis crack, the PCL removes them from the simulation. So the PCL will actually simulate the neutral axis shift in the pipe refractory section when the refractory fails. PCL also performs a fatigue analysis for occasional loads, seismic and wind. Analysis of pressure cycling is included with beam calculated forces and moments on branch connections and nozzles. Automatic combinations of stress ranges are evaluated per B31 equation 1D. With 3 alternating temperatures on branches and a Joule-Thomson cooling case, you have 4 temperature conditions and 10 possible stress ranges to evaluate on a node-by-node basis. When running the PCL, you enter only the 4 temperature cases and the PCL does the rest. There is no need in the PCL to try to guess at which load case gives you the worst stress range for every node in the piping system. The PCL does that automatically. Acoustic induced vibration is a known and difficult high-frequency problem. The PCL gives AIV guidelines, local and global stress calculations per IEC 50534-8-3 and 4 are all available in the PCL. FEA models are built automatically from Caesar models with the click of a button. We're going to look at that example in just a minute. The B31.3 2010 paragraph 320 introduces sustained stress indices as we saw earlier. The PCL develops these per guidelines in B31.3 and optionally per guidelines based on test results collected and evaluated by the Pollen Research Group. Path-dependent friction introduces a unique solution mechanism. We'll look at a few examples of those in a little bit where path dependence can result in large increases in calculated loads. To find more applicable I factors and K factors, a more detailed evaluation of the geometry is sometimes required. For welding tees in particular, the default I factors and K factors can very strongly be affected by the actual body thickness and details. The PCL has 3 different defaults based on measurements for these manufacturer-controlled components. So as far as the overall input is concerned, the PCL provides a forest and a tree look, along with a variety of typical graphical images of the piping, finite element models, and structural systems. In this next slide, on the bottom left, we see a typical forest view. All the elements are listed together in one spreadsheet, separated by user-recommended comments. On the right, we see a tree view listing all the possible element data, all the temperatures and pressures, all the thermal bowing details, all the material information, and all the unique ovalization specifications. The same is true in this next spreadsheet for Sif and flexibility data. The forest view is on the left, separated by optional comments. A right click on any row gets a tree view of all the particular data for any single Sif description. In the example shown here, the single Sif is for a B16-9 welding tee. Without additional input, a standard B31, B16-9 welding tee will be used in the analysis. In this example, the user wants the PCL to always use an FEA evaluation for stiffnesses and Sifs. This is a stainless tee. These tend to be relatively thin, and so the user wants to use the light T contour from the PRG measurements. The various T contours, light, medium, and heavy, are based on PRG measurements of actual welding tees. We talked about unique input. Head input can include data for cones, flat, dished, elliptical, and ASME heads. Welding and contour T thicknesses may be input if the manufacturer data is available. Like we talked about before, light, medium, and heavy welding T geometries are automatically available based on PRG measurements. OLED models are also available based on PRG measurements, or the defaults can be used from Appendix D for branch connections. Not only are FEA methods available for branch connections, but a variety of correlation-based methods are also included as intersection options. These include B31 improved methods as recommended in WRC 329. Also, the PRG method is recommended in the Peter Vu paper, and WRC 107 and 297 methods can also be used in addition to the FEA methods. Let's take a quick look at an example. In the piping system at the top, there are 64 welding tees total in two different sizes. The sizes are 4x4 and 6x4. The PCL senses that only two FEA models are needed for all the tees in this job. So the PCL runs and stores the two models in a superelement database in case they're needed again, and uses them for all 64 tees in the current piping analysis. So the superelement approach is shown schematically here. So the PCL finds two unique tees and runs the FEA analysis for them. It stores them in the database and then uses the two results from the database to populate all the tees in the model. This keeps the runtime for a job with 64 welding tees oriented in a variety of ways to a minimum. You may also notice when the PCL is loaded on your system the first time that there is already a database of over 3,674 10S, standard, and XS B16-9 welding tees, unreinforced fabricated tees, and OLEDs already in a mini-T superelement database that can be used without finite element rerunning. There are also a variety of finite element and correlation-based comparisons that are made automatically in the PCL during output, but we'll take a look at those interactively here in a minute. Superelement stress results for any of the possibly hundreds of developed load cases can be graphically or tabularly displayed. But it's definitely more interesting to see how this works when running the software. So let's start with a Caesar model and go through a typical analysis. So we'd like to start by importing a Caesar 2 neutral file. I'll open the PCL Gold, tell it I want to run a new job. It opens a blank spreadsheet. Go to Interface, Import, and import a Caesar 2 neutral file. That's the .cii file. There's a single Caesar neutral file in this folder. Select it, click on Open. I'm immediately given the opportunity to combine the operating pressures and temperatures if the ones I want to run for path-dependent loads are different than those set up by the Caesar file. We'll say no for this model because we've only got a single temperature. For multiple temperatures, large temperature fluctuations where gaps can close and friction can interact with the loadings, the order of the load cases can be very important, as we'll see in an example later, but for this model we'll say no. The Caesar model is imported. Any notes that are found during the import process are listed. You should go through those definitely for each model that's imported at least once. We'll assume this model is imported okay. There's an interactive CAD plotter that shows the model as I change it interactively. We want to run a finite element analysis for this model, so I'm going to go to the plot button, which runs the system plotter, which is a little heavier duty plotter. File name must be specified. I'll use the same file name as the Caesar imported job. And here's the system that we want to analyze. So this is the Caesar model. Here are the boundary conditions. If I turn on the restraint nodes, the two nodes that I've been asked to look at are the vessel connection at 301 and the vessel connection at 231. So there those are. Let's assume that this model is okay as is. Go ahead and make the run. This is a 350 degree temperature system with a 275 psi pressure, a lot of 4-inch pipe. Here's the output processor once the run is made. We'll look at 2D plots first. This graph shows the maximum stresses in the system for each load case. This is a little bit of an unusual curve or shape for this curve. The maximum stress is at the 9th load case, which is the hot sustained case. This sometimes suggests that the system is under-supported. The other high load case is in a hangar design case. So this is a little bit unusual. Let's go take a look at the stresses. Here's the stress history. We label that plot. This is essentially the 2D plot we saw before in 3D. If we look at it in this direction, we see that the highest stress is indeed at the last load case, which is the operating or the hot sustained stress case. But here are the stresses for all the nodes, for all the load cases in a single plot. Now, this is nice, and it gives us a good quick evaluation of the system, but we'd really like to know how close we are to our allowables. So we'll go to the sustained stress plot for that. Here's a sustained stress allowable. Here's the allowable surface at the top, and all the stresses for all the sustained cases for all the nodes in the model. We see there's a couple of nodes that are very close to the allowable. Let's turn on hover and go see what those are. That's node 675, so we'll be looking for that one. We'll turn off hover. But in general, the sustained stresses are all at least some below the allowable. Let's take a look at the expansion stresses. Here's the calculated expansion stresses and their allowables. The expansion stress allowables vary from node to node because the expansion stress allowable is a function of the maximum sustained stress at each node location, which we can see varies quite a bit. So the allowable expansion stress varies, as is seen in the surface. When we look at that plot from the side, we can see that most of the nodes are well under, or all of the nodes are well under the expansion stress allowables. So for this model, it looks like now at least we only have the sustained stresses to deal with. So let's go take a look at the 3D plots and the hot sustained case. So I'll come and plot code stresses for that case. Let me clear these first. So here's the code stresses for the 3D model. We'll animate that view. The colorization is in sync mode so that as the system deflects, the stresses go to their maximum values. That's sometimes not very helpful. We'll leave the stress contour shades on. Let's take a look at where the maximum values are, down around where the maximum displacements are in the vertical direction. So here's all the high stresses in the model. So they're all around this area due to this deflection. Let's take a look at what the vertical displacement looks like. So here's the vertical displacement. We're at about ½ inch down at this location. Let's put a shaded image on of the non-deflected shape. So we can see that sure enough this large valve string seems like it's not adequately supported. Let's see where our supports are. Now there's our supports. It's guided here, supported down here, but no other support. So it looks like we could use a support somewhere around this location. So let's turn that off. Let's get a simpler look at the model. So around node 710 we could put a Y support and potentially stop that displacement. So let's go ahead and do that. So that'll be one of the items that we'll change for the next run of this model. If we go and take a quick look at the reports we're usually interested in are the input process, which is just an input data listing, which of course should be checked before the model results are used for an evaluation. There's the beam calculated properties, which give all the evaluations of all the intersections, global coordinates, material lookups, Sif calculations, flexibility calculations, and so forth. So both of these reports are good for checking the models. There's a variety of restraint reports, a variety of stress reports. For this evaluation, we'll take a quick look at the Sif and Flexibility Factors. Here's the list of those. When we see Sifs like this, what we immediately expect is that we're using B31.3 Appendix D approach because we get in-plane and out-of-plane Sifs and no torsional pressure or axial Sifs. When we look for the two nodes of interest to us, 301 and 231, we don't see them in this list, which is typical for beam models that code up to piping or pressure vessels. Because the stress intensification factors aren't defined for the pressure vessels, they're not included in the analysis, and so the evaluation of those nozzles is not included in the pipe stress evaluation, which is not done here. So we'd like to be able to do that. That's part of what we'd like to be able to do with this next calculation. So we want to support node 710, and we want to come in and do a proper load evaluation for the 301 and 231 nozzles that are connecting to the vessel. So we're finished with the output review. Let's come into restraints. We'll come down and add a comment that we want to add weight support for displacement. Comments can be used for anything to help keep different parts of the model, different reasons that we add things clear in the input listing. The comments are carried along with it and are part of the input listing. So we want a Y support at 710. It's going to be allowed to move 0 in the minus Y direction. We'll essentially allow it to move freely in the plus Y direction, and we'll put a friction factor there of 0.3. That'll put the support in that we need. We'd also like to define the vessel nodes at node 301 and 231. These vessel connections are identical, so we can put both of them on the same data line. We have a pad reinforced intersection in a cylindrical shell. We could also have it in a sphere, an ellipse, a dished head, conical head, or a flat head. We want a pad reinforced intersection in a cylindrical shell. The pad thickness is 0.5 inches and the pad width is 3 inches. There's a lot of data in the Sif and K spreadsheet, as we discussed earlier in the webinar. So what we'd like to do is we'd like to look at the tree view for these two intersections. So here's the pad reinforced cylinder. I mistyped the pad thickness. We see that there, so let's change that. We definitely want to run the FEA, and we'd like a stress super element for this intersection. So let's click that on. We would like to always use FEA models for the stiffnesses and SIFs for these connections. And we haven't described the vessel yet. For a lot of piping connections to vessels, only the piping is described. We haven't described the vessel or the orientation. These are skewed nozzles, which tend to be a little bit more difficult to define. But all we have to do here is give the software some idea of the orientation of the vessel, and it can figure out the rest. So we'll tell it that the in-plane direction vector has at least a horizontal component. For vertical vessel, that should be sufficient. If it doesn't otherwise, guess okay. The vessel diameter is 144 inches. That's not entered anywhere because we don't have a vessel model in this piping system. And the vessel thickness is 1 inch. So we have a 1 inch thick vessel and a 4 inch standard wall pipe matching up to it. So we've got a 4 inch pipe of 0.237 inches up against a vessel of 1 inch. So this will be the finite element models that we evaluate at nodes 301 and 231. So we're finished with this. We'll apply those inputs and exit. When we come back, we can see that indeed the pad thickness error that I made earlier was corrected. Now we want to go in and say, yes, this model is going to include superelement calculations. Later, you'll find that when we turn on superelement calculations for all the branch connections in a particular model, it's convenient to be able to turn them all on or turn them all off from one place. That's what these two checkboxes here are for. So we want them on for this particular run. So we say OK. We've entered our supports. We've entered the stress intensification factor definitions for our nozzles. We should be ready to run. The software should go out now and see that the run is different this time from the last time. We've got a request for finite element calculations. The two nozzles are identical, so it will make one calculation for each nozzle and then apply it in the place where it's needed. We'll see two calculations go by quickly here. One is for loads through the branch. The other one will be for loads through the header. These are Markle type SIF simulations and flexibility factor simulations. So the finite element calculations for those nozzles were just made. They were inserted into the model. The post-processing of the finite element results was just done, and now the output processor appears. We'll go take a quick look at the Sifs and flexibility factors calculated here. So here are the Sifs calculated for nodes 231 and 301. Here are the typical B31-3 type Sifs for in-plane and out-of-plane. These are fairly low values. We get a torsional value that's less than 1, which is typical for piping. A value of 1 will be used here. For the axial loads, we have a Sif of 2, which is a little bit high, but not very high. For pressure, we have a very high stress intensification factor of 16. So what we want to know is this pressure Sif that looks so high reasonable or not reasonable? We remember looking at the stress indices earlier, and what we saw was that there was a Section 8 Division 2 pressure stress calculation that was based on an index and the nominal stress of PD over 2T, where D and T are the diameter and thickness of the vessel. We have a pressure stress component given to us for any run side piping, and we have a pressure stress component given to us for any branch side piping. If we use the B31 code equations for the run side or the branch side, those are the nominal stresses for the B31-3 equations are given to us in terms of PD over 4T, not PD over 2T, which is just a nominal definition. You can use either one. The stress in the nozzle due to the pressure is the stress in the nozzle due to the pressure. They, however, give different nominal bases, so we expect that the I factor are going to be different, and that's indeed what we see here. So if we take a look at the stress calculations or these factors for this particular nozzle, and we assume that the pressure stress for the vessel should be the same as the pressure stress for the nozzle, here are the equations that we end up with. And these equations essentially give us a geometry factor that relates one stress intensification factor to the other. So the geometry factor to get from Section 8 Division 2 to B31 is essentially 2 times the diameter ratio times the thickness ratio. And for this geometry of interest, that geometry factor is about 17. So if we go back and make a finite element calculation using the Section 8 Division 2 approach, we should have an I factor using the Section 8 approach of around 1. Let's go see if we can show that that's the case. Using the PCL, we have an FEA button. The FEA button gives us access to all of the intersections or all of the FEA models that are used in the PCL. We'll pick one of these branch connection models because they're identical and open it in Nozzle Pro. This warning message tells us that any modifications we make in Nozzle Pro, which we can make, won't be reflected back in the PCL. Here's Nozzle Pro. Here's our 144 by 1 by 4 inch branch connection. We're going to make an FEA run for that. It'll go out, perform the analysis. Here's the decomposition, forward and back substitution. Post-processes all the results. Open the output in this left panel. So here is the Nozzle Pro calculation. The Sifs show that the pressure Sif is indeed about 1. If we take a look at the tabular reports, we see that for exactly the same finite element model, the pressure stress intensification factor calculated using PD over 2T as the nominal pressure stress gives us a Sif of 1, or a stress intensification factor of 1. If we make the same calculation using the B31-3 nominals, we get a pressure stress intensification factor of 16. So it's very important when we use pressure stress intensification factors and try to get applicable data from other sources that we make apples to apples comparisons. That's one of the reasons that I wanted to go through this here, because these high numbers sometimes cause alarm, but when you look at them in terms of the nominal stress basis, this makes perfect sense. The superelements give us, or what we talked about in the beginning, the superelements let us take a look at the stress distribution in the finite element models. Okay, here is the superelement output screen. We'll take a look at the load cases on a per load case basis. Let's take a look at the stress distribution in that hot sustained case. Here's the finite element models and the stress distributions. Let's linearize those so they make a little more sense to us. So this is the finite element calculation and the output results. There's membrane stresses, bending stresses, membrane plus bending on the inside, membrane plus bending on the outside. So let's linearize those again. If we take a look at the highest stress area, we can see it's at the edge of the pad here, as we might expect. Now this is nice, and the color plots are interesting, and they give us reasonable ideas that the calculations are okay. But what we'd like to see is how the B31 calculations compare to the finite element calculations. We come down to FEA stress results. We see that there's an FEA B31 equivalent stress report. So if I ask for that, what I get is I get an FEA calculated membrane plus bending stress and the beam stresses based on the stress intensification factors. So where the beam stresses equal the FEA stresses, we think we're getting a good comparison, or at least we're getting a good comparison to the membrane plus bending stresses. So the membrane plus bending stresses for the finite element calculation for load case 2 were 23,000. From the beam analysis, 23,809, very close. Same for load case, well, 4 is not very close. Same for load case 5, same for load case 6. What are these cases? There are a variety of places we can go to get load case reports. Let's get one from the text output processing. So for cases 4, we don't have a very good comparison between the beam calculated results and the finite element results. Case 4 is a sustained case. For case 5 and 6, we have pretty good correlation. So the FEA model, the membrane plus bending stress from the FEA analysis, agrees very well with the PD over 4T plus IM over Z calculation from the beam analysis or from the beam results. Case 7, we've got reasonably good agreement. That's a return to weight only case. In cases 8, good agreement, the range case, but case 9 is not very good agreement. So what's the difference between cases 2, 5, 6, and 8 and cases 4, oh that's okay, and 9? So 4 and 9 each contain pressure. One of the items that was mentioned earlier in the stress calculations is what do we do with the pressure stress intensification factor? In the engineering details portion of the PCL, there's a variety of options available for both the stress calculations and for the I factors and how the I factors are used. The default value doesn't use a pressure stress intensification factor for sustained and occasional stresses. If we want to use a pressure stress intensification factor for sustained and occasional stresses, we have to check that box. So if we check that box and remake the run, so now what we're doing is we're remaking a pipe stress calculation that has 2 finite element model results in the run. Just clicked on run, here's the post processor, here are results. Let's go back to the report that we had questions about, the FEA and B31 equivalent stresses. And now we see that the stress cases align. So if we want to include pressure as a stress intensification factor for our sustained and occasional stress analyses, we will be comparing to membrane plus bending stresses from a finite element model. I hope this last discussion about pressure stress intensification factors was a little bit interesting. We can see now that if we use the IP, which is the pressure stress intensification factor, times PD over 4T for the stress calculation for sustained and occasional loads, that we should get a stress that's about equal to the FEA membrane and bending stress. If we use the code suggested 0.75 I times IP times PD over 4T, we should have about 75% of the membrane in the bending stress. There's another option here, though, that suggests raising IP to the 1/2 power times PD over 4T, and that should be used for sustained stresses and occasional stresses up to a D over T of about 60. So where does that come from, and which of these options should we use? I think the answer is that if you use the default and don't change the default, you'll likely get improved I factors for external loads and pressure for fatigue, but not get intensified pressure stresses effectively for sustained or occasional stress calculations. If you activate the use of the pressure I factor for sustained and occasional stresses, like we did in the last example, and use the 0.75 I from the code, the thought is that you'll be about 25% too low in some cases and perhaps a little bit too high in others. The key thing to remember for sustained and occasional stresses is that usually the failure mechanism is collapse, and so we want to know what part of the I factor can be used to predict collapse in a branch connection. High local bending stresses tend not to contribute as much to collapse locally as high membrane stresses. The test results suggest that high I factors should be derated some due to the high bending component. Pressure is potentially the odd loading out, though, in this sense, in that pressure loads can actually increase the collapse factor. But more on that in the next webinar. I need to perform one more calculation with this PCL model. The piping system and the vessels are in Southern California, so I'm going to specify seismic loads, and I need to get the G factors. So if I come down and enter the zip code for my site, 92112, 92112, that's in San Diego. Let's see, somewhere here. That's where the facility will be located. So I'm going to look up the values for that zip code and then use those. So we have the G load, so we'll export those and exit. So now we're ready to reperform that analysis with the seismic components, or with the seismic loading components. That's all we needed to do to get the PCL to put those in for us. Here it's making the FEA calculations for the additional seismic load cases. It's the output processor. So now we've just remade the run with the two finite element model nozzles in it. Let's take a look at the load case report. There are now 33 load cases. First two are the hanger cases. Here's the operating case. Here's the hot sustain. And now here are all of the additional seismic cases that were entered for us after we just entered the zip code. You'll notice that there's several range cases that are performed for seismic fatigue evaluation and for seismic primary load evaluation. We looked at the text reports before. Text reports also make 3D plots available for us. We can get the occasional stresses, or the occasional stress summaries there also. Here are the plots that we saw earlier. Here are all the occasional cases now set up for the seismic loading for all the nodes. Some of them we can see are over the allowable. And as we might expect, those occur at our vessel nozzles. We talked about the I factor and K factor calculation spreadsheet in the PCL. That's available under the Utilities button. And in additional programs, PRGB 31 waste, YDR, I factors, and K factors. That spreadsheet can be opened. And any run pipe and branch pipe diameter entered, the Compute Update I and K factor calculation button pressed, and all the I factors and K factors from the Peter Vu 0702 ASME project are displayed. B31I and K factors, of course. B31.3 right now doesn't have any K factors, but here are the branch and the run side I factors. Here's the NC and NB I and K factors. K factors for unreinforced fabricated Ts are available in NB 3600. Here are the Denorsky-Veritas I factors, Weiss I factors, and K factors from the Weiss-Epri work for both unreinforced fabricated Ts and pad-reinforced fabricated Ts. Here are the Widera I factors and K factors for unreinforced fabricated Ts from WRC 497. Then here are the calculated stiffness values used from the PRG calculations. So this is a very handy spreadsheet to come down and use for comparison of K factors between the different methods and for calculation of the actual values of the K factors so that you can come here and make the determination that we were talking about earlier to decide if the K factors should be used in the analysis. We talked a little bit about acoustic induced vibration. Here's one of the calculators that are helpful in making those determinations. For a 48-inch length of 16-inch 375 wall pipe, we can make the calculation for the natural frequencies and then come in and plot those. What we'll see from the plotted shapes, let's put the natural frequencies on those. From the plotted shapes, here are beam bending modes at very high natural frequencies. And these are frequencies that you may see in an acoustic induced vibration situation. Here though are, so these are the beam bending modes. Plane sections remain plane. Here are the acoustic induced vibration or shell bending modes. So these are the modes that you'll calculate in a 6 degree of freedom pipe stress program like Caesar. Here are natural frequencies that you can calculate in an 18 degree of freedom pipe stress program like the PCL. Fortunately, they're orthogonal and don't interfere with these mode shapes much. But this is a part of what needs to be done when acoustic induced vibration is evaluated. The classic path-dependent friction problem is shown in this slide. The piping system starts at an essentially zero stress state and then heats up. The friction resists the displacement and loads are developed in the pipe that act back on the vessel nozzle. When the system cools down again, the friction loads change sign and pull out on the vessel nozzle with essentially the same load. The stress range due to this effect is doubled what would be calculated by looking at a weight to operating case alone. Here's a situation where a seismic or wind event or some other thermal upset condition acts before the operating case of interest. The occasional or upset condition, along with gaps, causes the pipe to move and then to remain fixed in place due to high loads and friction that were overcome due to the upset event, but that are not overcome during regular operation. In this case, equipment loads can be higher because the standard operating case thermal expansion is now pushing against a piping system that is not starting from its neutral position and that is fixed in place due to friction. Let's take a look at another fairly typical path-dependent friction case that can be analyzed in the PCL. Here's the system. It's a modestly long transfer line, not too long, I guess. Small branch to be protected, gapped support to protect the small branch from the X direction thermal expansion coming from the anchor at this control valve skid. Piping goes to another anchor at another skid or station of some kind. So we'll expect X displacements along this run, or large X displacements along this run, large Z displacements along this run, and some kind of opening in the X and Z direction at the elbow. There's friction at all the supports. Let's go ahead and make that run. Here's the results. Let's take a look at the 3D plots of this. So there's the animated displaced shape as kind of expect. Piping is bending about the gapped support here. Put the restraint node numbers on it. So it's moving in the purely horizontal direction as you'd expect from a piping system sitting on all these supports. So we've got friction loads acting along this leg and friction loads acting along this leg. So let's go take a look, say, at the node 20 restraint loads. So I'm going to go to the table view. Let's go look at restraint loads for the operating case. Let's turn the filter on and select node 20 so that that's all we look at. And we can see that the loads acting on the support due to the pipe are in the minus X direction. So if we go back to the 3D plot, the loads on the support at 20 are acting in the minus X direction. Let's check the displacements in the X direction at 20. So I'm going to grab the thermometer tool and move it over the support location at 20. And what we can see is that the displacements are in the plus X direction, but yet the reaction loads on the support due to friction are in the minus X direction. So the question we want to ask is, how can that happen? What happens at node 20 is that the pipe system begins to slide in the plus X direction until the 2.5-inch gap at 26 out here closes to protect the branch pipe. This is so far so good for a program that uses total displacement to determine the direction of the friction loads. By the time the gap closes, a good part of the X run of pipe is sliding in the plus X direction through 1 to 2 inches of displacement, and the loads acting on the supports are acting in the plus X direction. When the gap closes at the end of the pipe at node 26, the supports close to 26 continue moving toward 26, but the supports further away, for example at node 20, stop and begin moving in the minus X direction. The total displacement at node 20 is still in the plus X direction though. This is shown in the diagram at the top of the slide. The block in the figure slides to position 2, stops, and then reverses direction and slides to position 3. When the block shifts direction at position 2 and begins sliding again, the direction of the friction load on the restraint switches also. For programs that base the direction of the friction force on the total displacement of the restraint, for cases like this as shown in the top figure, the loads will act in the wrong direction. For the example problem, since the gap was closed and some of the friction loads changed sign, the reaction loads at point 26 increased. Programs that don't evaluate the path dependence of the load won't see that the sign changed and can underestimate the load. Using a program based on total displacement for the friction load directions, the reaction load on the gap support at 26 was calculated to be 8,800 pounds. Using the PCL, which accommodates the path-dependent change in the load along the X run of pipe, the load was 14,000 pounds, or 1.6 times greater. Let's take a look at the lockup friction model that can cause theoretically almost unlimited increases in support reaction loads. For the case shown above, the leg from E to F heats first, closes and locks the guide at B. When the line from A to B subsequently begins to heat up, the guide at B is locked due to friction and high loads develop. It can otherwise occur in more complex systems when one part of the system heats before another part and closes gaps in the model which do not slide. Let's take a look at one of these systems where the order of the load cases results in whether the system support locking occurs or not. These are results that cannot be simulated in a program that does not include a path-dependent solution process. So let's take a look at how this is simulated in the PCL and what effect it can have on reaction loads. We developed the simple Huygens model because the result can be calculated manually, and the users can prove to themselves that much larger reaction loads can be calculated due to the path dependence of the solution. Larger reaction loads in this model are due to the thermal path dependence, gaps, and friction. System, as we can see, is guided in the z direction with gaps at nodes 3, 4, and 5. At node 6 there's a z restraint only, and at node 1 there's an anchor where we're interested in the y moment or the stresses. There are two thermal cases. One is with the entire system hot, and the other is where the branch leg from 6 to 3 only is hot. So temperature case 1 is where the 6 to 3 branch is hot, and temperature case 2 is where the entire piping system is hot. We'll run this system two ways. The first case will run with weight cases in between each thermal case. This will simulate the non-path dependent friction solution because the gaps open without thermal load, and so there's no dependence of one thermal case on the other. In the second method, we'll run the path-dependent solver and go from thermal case to thermal case, and see that in the situation with the Huygens model, the first thermal case will bind the supports in the z direction and cause a doubling of the stress in the second thermal case. So let's run the first thermal configuration. We'll go to the 2D plots. We'll see that we go from weight to temperature to weight to temperature 2, so weight, temperature, back to weight, and the high stress in the model is about 10,000 psi. Now we'd like to go back and go from weight to temperature 1 to temperature 2 and see if the stresses change. There are a variety of options in the multiple load case form in the PCL for ways to manipulate the load cases. Here we remove the 1 to eliminate the return to the weight cases in between each of the thermal cases. Remake that run. Stress before was 10,000 psi. Now when we go from one thermal case to the next, because of the thermal locking of the restraints, we can see that the maximum stress in the system has doubled. We're preparing separate presentations for acoustic-induced vibration, refractory and glass-lined piping systems, pressure I factors for fatigue and sustained stresses. When you have a tough diagnosis, you go to a second doctor. When you have a tough piping analysis, I hope we might have convinced you that you should go to the PCL. As an aside, for anyone that lives in the 92112 zip code, that's not an actual location for the piping and vessel we were analyzing, so no one is building a chemical facility near your home. We'd also like to emphasize that experience and judgment trump large FEA models and weeks of piping model building. You have to know what to expect and build models to validate that anticipation. You can adjust the density of a finite element mesh so that results are within 5%, but we do not want to pretend that we're predicting the stress for a piping system in a fossil or a chemical plant to within 5%. And that has nothing to do with the software that we're using. A recording of this webinar will be on our website at www.pollen.com. If you would like any more information on unanswered questions, scheduling a demonstration, getting additional training, or a particular design or modeling issue, please let us know at www.pollen.com. Send an email to sales@pollen.com or contact our sales group at the number given below. Thank you very much for your time.